Good morning, student. Today I talk on most probable macrostate, relation between thermodynamic probability and mathematical probability, relation between probability and thermodynamic probability. But this is the third lecture, and we know in previous two lecture we know probability, zero probability, total probability, macrostate and microstate, thermodynamic probability, most probable macrostate. We know the probability is nothing but the ratio of the number of happening event to total number of occurring event, and the value of probability lies between 0 and 1. The probability of happening event considered as 1 and the probability of non-happening event, that means the fail event, is 0, that is, and it is denoted by letter P. That means the P lies between 0 to 1. Then what is zero probability? The zero probability which is the impossible. For example, take die. In case of die, 6 faces 1 to 6 and the probability of 7, because 7 face is not present in case of die, therefore its probability is 0. That means the probability which is impossible, that is called the zero probability. What is total probability? Here the value of total probability is always 1, because it is the sum of probability of happening event and the probability of fail event. Take sum of both, we get its value is always 1. Then what is the macro and micro state of the system? Suppose we take the 4 distinguishable particles. Here A, B, C, D are these are the distinguishable particles. Your aim is these 4 particles distributed in 2 compartments, first and second. What are the possibilities? Here first possibility is take the here in first compartment 0 particle, in second compartment take the total 4 particle. Then the next possibility is take first, take 3 second, take 2, 2, 3, 1, 4, 0. These are the possibilities, and these possibilities is nothing but macrostate of system of 4 distinguishable particles. That means how many macrostate? 1, 2, 3, 4, 5. Here these are the compartment. This is not the macrostate. That means how many? 1, 2, 3, 4, 5. 5 number of macrostate. In case of 4 number of particle, take into compartment. That means suppose this is the n number of particle. Therefore how many macrostate of the system? That is the n plus 1. That is 4 plus 1 is 5. 5 number of macrostate is in system. Then these particles are distinguishable. Suppose here take 0 and 1. The 0 is in first compartment, 2 is in second compartment. Then for this combination, how many possibilities? That is take 0 in first and take A, B, C, D in second compartment. Therefore only 1 distribution possible. In case of second, take the 1 number is in first, 3 is in second. That means take out of 4, 1 is here, the B, C, D here, B is here, then A, C, D is here, C is here, then the A, B, D is here, D is here, the A, B, C is here. That means for this the 4 number of possibilities, 4 number of ways of distribution of distinguishable particle in 2 compartment. Therefore for this here the 6 number of possibility. That means take first A, B in first, C, D second, A, C first, then the next 2 is in second compartment. In this way, the 6 number of macrostate we know already. For this again same, and for this the one possibility. Therefore, here observe. The 4 distinguishable particles distributed in 2 compartments. How many possibilities? These are the 5 number of possibilities. Right? That means 0 in 1, 4 in second. In this way, and in this macrostate, the 4 number of possibilities. Take first, another 3 second. Take second, another 3 is in second. Take third, another 3 here. Take fourth, another 3 here. Therefore, the how many number of distribution? 1, 4, 5, 5, 6, 12 and 4. That means the 16 number of possibility. Therefore, 4 number of particle is in 2 compartment. That is 2 to the power 4 is the 16. That means 16 number of microstate of system which consists 4 distinguishable particles in 2 compartments. Right? That means the what is formula? This is for 2 to the power n. In simple way, c to the power n. C is the number of compartment and n is the total number of particles. We get a number of microstate, and here n plus 1 is nothing but macrostate. Right? Then we know macrostate, we know microstate. Then here the next is thermodynamic probability. Here in case of 3-1 distribution, first compartment, second, 4 number of microstate. In case of 2-2, here 6 number of microstate. Right? When the 4 number of distinguishable particle take in 2 compartments, here observe. This is the thermodynamic probability. Here the thermodynamic probability denoted by letter W. This thermodynamic probability is nothing but number of microstate corresponding to macrostate of system is nothing but thermodynamic probability. What is thermodynamic probability of this macrostate? 4. Here this is the 6 for 2 macrostate. That means what is thermodynamic probability? Thermodynamic probability is nothing but a number of microstate consist particular macrostate called as thermodynamic probability. Then here observe 3-1 is the macrostate. It has the 4 number of microstate. 2-2 is the macrostate. It has 6 number of microstate. That means what is most probable macrostate? The macrostate. It has maximum number of microstate of the system. Here observe 3, 4 microstate, 2, 6 number of microstate. Therefore, this is called most probable macrostate. Most probable macrostate. 2 macrostate is most probable macrostate. Right? Then relationship between thermodynamic probability and mathematical probability. Here we know thermodynamic probability denoted by letter omega, and its value is greater than or equal to 1 always. And we know thermodynamic probability is nothing but number of microstate related to macrostate called as thermodynamic probability. And the mathematical probability is always less than equal to 1. Many times the ask 1 mark question in exam in question 5, what is the difference between mathematical probability and thermodynamic probability? the value of thermodynamic probability is always greater than equal to 1, and the value of mathematical probability is always less than equal to 1, right? Then the relationship between, we know the relationship between thermodynamic probability and mathematical probability, and then the here relationship between probability and thermodynamic probability. Here this probability is directly proportional to thermodynamic probability. We know probability, definition of probability, it is the ratio of number of events happening to the total number of events occur. What is thermodynamic probability? The thermodynamic probability is nothing but number of microstate corresponding to macrostate. Therefore, it is P is equal to small p W. Here, small p is nothing but 1 upon C to the power n. Here, C is nothing but number of compartment, and n is total number of particles in the system. Therefore, P equal to omega by C to the power n. C is number of compartment and n is the total number of particles. Also, omega is nothing but, we know the omega is nothing but NCR, and NCR is nothing but n factorial, r factorial, n minus r factorial, right? Therefore, here, the probability is nothing but P is nothing but 1 upon C to the power n, NCR, that is P equal to 1 upon C to the power n, NCR, n factorial, r factorial, n minus r factorial. This is the probability of the system, or probability of the macro state of the system. Here, suppose take this is the macro state. Also, you know, in this case, the total number of microstate are 6. We know already examples. Here, P equal to, when you put this formula, P equal to 1 upon, how many compartment? 2 compartment. How many number of particles? 4 particles. Total number of particles 4 factorial. Here 2 factorial. This is the probability of this macrostate for the system of 4 number of particles, which is distinguishable. And today stop here.